Sitten kun se sanoi, vai nyt kokeilla ilman niinku pointti. Kertonen niin, että se siirtyy. Ja se tarvitsee. Sitten se kertaa yhden saman.
first of all, ask the questions, well, what do we need the skin of a car for anyway? What's it there for? Does it have to be made out of metal? Do we have to make it always in the same manner? Or is it there for different purposes than we thought? In reality, the aspects of crash and stiffness and ride handling can be handled in a space frame type vehicle entirely without the skin. And therefore, to go away from a metal skin and to have a skin that offers different capabilities, can move, can do things that a fixed rigid structure couldn't do, can be lighter, made out of materials which require less energy to make them. That's something that the GINA Light model brings as a question. GINA is an acronym, a set of letters that stand for geometry, shapes, and function, how things work, in N is a way of saying infinite number, of adaptations, meaning there's a lot of change possible. This started a whole chain of ideas within the company here that GINA became not just a model that became a shape or just about cloth as a skin. It became about a thinking process, a philosophy that said, let's do things differently. Let's let materials talk in a different manner. And let's let tooling be a different issue instead of just the way to give us form. Well, one nice thing about GINA is the materials kind of lead the way. It doesn't take very much and you get an idea exactly what this car is going to be like. For instance, to get an idea what the sculptural form is between a fender and, let's say, a wheel arch, you really only need a line around the wheels and a line more or less where you want the fender to be, and you'll let the material do the talking in between. And then, just like you would if you were getting a suit made, you made the first mock-up, you made the first forms and patterns, you sewed it up, you tried it out, made another one a little bit closer, and when you finally got the final one, zip, you put it on. It takes about 2 hours to put the skin on this car. Emotion is really the added value to this. I mean, one way is saying you get better function or you get better alternative ways of doing things, but really we want to achieve a higher emotional plane out of this. And then finally, and I think this is to me one of the most importantly, and that is the level of humanistic content that we can bring with GINA in. GINA should be about the human in the loop, the human way of doing things. The GINA philosophy, in its short form, is about being flexible. Thinking flexible, acting flexible, context over dogma. That's it.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of, well, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? Well, that's really, 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 really small. And you know what? It gets even more crazy. Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a 2-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium with the nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth. So if everyone on the Earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of a nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, it would have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small. Think atoms in a grapefruit, like blueberries in the Earth. The nucleus is crazy small. Now look inside the blueberry and blow it up to the size of a football stadium, and now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. Think of putting all those cars in your 1-foot box. I think I'm tired.
The world seems almost infinitely complicated, made up of thousands, if not millions, of different materials. Throughout history, people have tried to collect, categorise and analyse them, to find some underlying pattern that would help simplify this seemingly incredibly complicated world. Now, at the dawn of the 21st century, we've made some progress to achieving that long yearned for simplification. With the use of particle accelerators, we are starting to understand the nature of the world around us. These machines have revealed a whole array of particles which, we believe, may be the fundamental building blocks of matter. But back in the 19th century, scientists thought that everything on Earth was made of just over 80 elements. These elements were famously arranged in a periodic table by Dmitri Mendeleev. At the time, it was thought that elements were made of indivisible spheres called atoms. But each of the elements behaved in a different way. Did that mean that there were 80 different kinds of atom? And if so, what made them different? Were they different shapes or sizes? Or maybe the atoms were divisible. Maybe they were built of even smaller objects. It was here in Cambridge that the first clear evidence for smaller objects inside the atom was found. Many of the great scientists of history have walked these streets, and one of the greatest was J.J. Thomson, who became the director of this, the old Cavendish laboratory. In 1896, Thomson had just got his hands on this new piece of kit. Now, it's essentially a particle accelerator. When this plate's heated, particles are emitted. They're accelerated by these electrodes. They pass through these two plates, across which you can apply a voltage, and they hit the end of the bulb here on a screen which glows, so you can see the beam. Now, this is a modern version of Thomson's apparatus. Again, we've got the particle accelerator, and there's a screen in there so you can see the beam glow. What Thomson did was he varied the voltage across the plates, and he measured the amount of bending as the voltage changed. That allows you to deduce the mass of the particles in the beams. Now, the lightest known particle in Thomson's day was the hydrogen atom. But Thomson found from these measurements that the particles in this beam are almost 2,000 times lighter than hydrogen atoms. Thomson had discovered the first subatomic particle, the electron.
The electron owes its practical utility to its smallness. It might apparently Shakespeare say, "My use is great because I am so small."
The electron was the first discovery of a fundamental particle, and it is interesting to realise that more than 100 years later, the electron is still, to the best measurements we can do today, a fundamental letter of nature's alphabet.
We can use electrons as ways to probe materials and look at the structure in electron microscopes or in big machines like this accelerator behind me. Pretty much all of everything we do in the 21st century depends on understanding the properties of electrons.
Thomson had discovered that the atom is not the fundamental building block of matter. There are smaller objects inside. So atoms could no longer be thought of as hard, indivisible spheres. But how do the electrons fit inside the atom? Thomson suggested that the atom was something like this muffin, with the negatively charged electrons embedded in a positive body. It would be a student of Thomson's that proved him wrong. The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator. So he used the decay of radioactive elements to produce his beams of particles. This is Rutherford's original desk. And in fact, if you hunt around a little bit, you can detect traces of radioactivity 100 years later. Rutherford asked two of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil and see what happened. So imagine these tennis balls are the alpha particles. Now if the atom were, as Thomson had suggested, a kind of amorphous blob, then you'd expect the alpha particles to pass right through. And that's indeed what happened to most of them. But to their surprise, they found that around 1 in 8,000 bounced right back. After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun.
Today, we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are, but we can predict that they reside in distinct shells around the nucleus.
Rutherford's alpha particle scattering experiment was remarkably direct and simple, and it showed the nature of what the atomic structure is. By the way the alpha particles bounced off the atom, he worked out where the positive charge of the atom lives.
Rutherford had come to the astonishing conclusion that most of the atom, and therefore most of what we think of as ordinary matter, is in fact empty space. So if this apple were the atomic nucleus, the electrons would be a kilometre away.
After discovering the nucleus, Rutherford continued doing experiments, firing particles at different targets to delve into the structure of the nucleus itself. By 1932, Rutherford and his colleague James Chadwick had found that the nucleus is made of two kinds of particles, positively charged protons and electrically neutral neutrons.
The discovery in these experiments of neutrons, uncharged atoms of mass 1, has proved of great significance and importance, and has given us a much clearer understanding of the actual structure of nuclei.
Less than a century after Mendeleev published his periodic table, scientists had arrived at a seemingly beautiful simplification. All this is made of just three fundamental particles: the proton, the neutron, and the electron. Now, this was a giant step forward in our understanding of matter, but there were still phenomena that couldn't be explained in terms of just these three particles.